welcome to the Bodhi Academy. My name is Amisha Classo, and in today's video we'll continue with our class 11 chapter 6 equilibrium. So in today's video we will learn about the two types of equilibria that we have, that is the homogeneous equilibria and the heterogeneous equilibria. To begin with, let's talk about the homogeneous equilibria. So in a homogeneous system, we know that all the reactants and products are going to be in the same phase. Now when we refer to phases, we are talking about the states of matter. It may be solid, liquid or gaseous state. So here what we are saying is that in a homogeneous system, in that all the reactants as well as the product are going to be in the same phase. That is, they are going to either be in gaseous state throughout, liquid state or in the solid state. For example, in the gaseous reaction of N2, that is nitrogen gas, plus H2 hydrogen gas, giving us NH3, that is ammonia gas. Here all the reactants and products, they all are in homogeneous phase, that is all of them are in the gaseous state. Similarly, if we look at this reaction, here also we have CH3COO C2H5, which is in aqueous state, and we have water which is again in the liquid. Aqueous and liquid means it's in the solution form. Then we are having CH3COOH again in the aqueous form and C2H5OH again in the aqueous form. So here also all the reactants and products are in the homogeneous solution phase. Now we shall consider the equilibrium constant for some homogeneous reactions. So equilibrium constant in gaseous system. So far we have expressed equilibrium constant of the reactions in terms of their molar concentration of reactants and products, and we have used a symbol of Kc, that is denotes the equilibrium constant. Now for reactions which involve gases, however, it is usually more preferred to express the equilibrium constant in terms of their partial pressure. Now we know that the ideal gas equation is PV equals to nRT, where P equals to N upon V RT. So here P is the pressure that is given in pascals, that is PA. N is the number of moles of the gases. V is the volume that is given is in meter cube, and T is the temperature that is given in Kelvin. Therefore, N upon V is the concentration that is expressed in terms of mole upon meter cube. Now if concentration is C is in mole per liter or mole liter dm cube, and P is in bar, then we can say that P equals to CRT. So this N upon V which is there, we are saying it is the concentration. So we have directly substituted this with C over here. So we get a new equation, that is P equals to CRT. We can also write it P equals to concentration of gas. Again this box brackets indicate the concentration of the gas into R into T. R is 0.0831 bar liter per mole Kelvin. Now at constant temperature, the pressure of the gas will be directly proportional to the concentration. So here pressure is directly proportional to the concentration of the gas. Now for reaction in equilibrium, say we have H2I2 giving us hydrogen iodide. So we write Kc equals to concentration of product upon the product of concentration of both the reactants. And here we have to take the mole value, as in what is the stoichiometry it is raised to. Now same thing if I have to write it in terms of the pressure term. So pressure of Hi the whole square upon pressure of H2 into pressure of I2. So further I can say that pressure, this will be equal to concentration of Hi product into RT, and then same way I can write the rest of the terms. Same in the this format, that is a product upon the reactants, we are going to substitute it, and we get here Hi gas raised to the whole square upon RT the whole square, H2 gas into RT dot I2 into RT. So here we will get Hi, this R and this R will get cancelled. So here Kp will be equal to Kc. So if you see here, this is R square. So this and this square will go, and this RT and this RT will go. So we will get the same equation. Now this equation is also equal to Kc. So for this example, what we can say that Kc is equal to Kp, because we are getting both terms are same. However, this is not always the case. For example, in a reaction of N2 plus hydrogen giving us ammonia, here we write again the equation, that is NH3 twice raised to square raised to 2 upon Pn2 into pH2 the whole raised to q. Same way now we substitute this. Okay, so on substitute, so here what will happen, we will have, if you have to write a Kc equation of this for better understanding, we'll write, sorry, NH3 concentration raised to square upon, will have H2 raised to 3 into N2. Okay, this same equation in terms of Kp will be this with reference to RT over here. Now in this case what will happen, this R will get, RT will get cancelled, this RT will get cancelled, this one will get cancelled, and this one will get cancelled. So we will have over here the equation that we will get is NH3 raised to 2 upon N2 H2 cube and RT square. Now these two equations, they are different. So here in such cases what we can say that our Kp is not equal to our Kc. Okay, so here our, so if we rearrange this and we try to write it in a better form, we can write it here. What will happen, this whole part remains same, so this will be equal to Kc, only this part will go as RT minus 2. So our Kp will be equal to Kc, because this whole part is basically our Kc, only this part is different. This if I take in the numerator, then it will become RT raised to minus 2. So here such cases are possible wherein our Kp and Kc are not going to be equal. Next, let's talk about the heterogeneous equilibrium. Now heterogeneous means the phases are going to be different of the reactants and the products. So equilibrium in a system having more than one phase is called a heterogeneous equilibrium. So the equilibrium between water vapor and liquid water in a closed container is an example of heterogeneous equilibrium. Simple example we have taken here is that the equilibrium that is attained between the water vapor of the liquid water in a closed container and with the water that is present in liquid state. Now in this example there is a gas phase and a liquid phase. Now in the same way, equilibrium between a solid and its saturated solution, say we have calcium hydroxide, that is the solid, plus aqueous solution will give us some water is there, so it will give us what, calcium ions plus hydroxide ions. Now this is a heterogeneous equilibrium. Now heterogeneous equilibria, they often involve pure solids or liquids. Okay, now we can simplify equilibrium expressions for heterogeneous equilibria involving a pure liquid or a pure solid. As the molar concentration of a pure solid or liquid is constant, that is independent of the amount present. So in the other words, if the substance X is involved, then X of solid and X of liquid are constants. Okay, whatever the amount of X is taken, contrary to this, X gaseous and X aqueous will vary as the amount of X in the given volume varies. Now let us take a thermal decomposition of calcium carbonate, which is an interesting important example of heterogeneous chemical equilibrium. So now here what they have said is that we know that here they are saying that the solid which is there, the concentration of the solid and concentration of liquid are going to be constants. Okay, because they mainly involve solids and liquids. So if there is anything apart from solids and liquids, then their concentration is going to be defined. One simple example we are going to talk about here is the calcium carbonate example, that is the thermal dissociation happening of it. So we have calcium carbonate which is thermally getting dissociated into calcium oxide and carbon dioxide. Now on the basis of their stoichiometry, we can write a Kc, that it is the product of concentration of concentration of the products upon the concentration of the reactants. Now since here we are saying that the solids are going to be, both the solids are going to be constant, we can say that Kc will be only related to the concentration of the CO2, that is the gas that is present. So even in terms of partial pressure, we will talk about partial pressure of carbon dioxide. This shows that at a particular temperature, there is a constant concentration or pressure of CO2 in equilibrium with calcium oxide and calcium carbonate. Experimentally, it has been found that 1100 Kelvin, the pressure of CO2 in equilibrium with calcium carbonate and calcium oxide is 2.0 into 10 raised to 5 Pascal. Therefore, equilibrium constant at 1100 Kelvin for the above reaction is going to be 2 into 10 raised to 5 Pascal per 10 raised to 5 Pascal, that will be equal to just 2. So similarly, in the equilibrium between nickel and carbon monoxide and nickel carbonyl used in purification of nickel, we get a similar kind of a relation that occurs. So it must be remembered that for the existence of heterogeneous equilibrium, pure solids or liquids must be present at equilibrium, but their concentration or partial pressures do not appear in the expressions of the equilibrium constants. So now let's talk about some of the applications of equilibrium constants. So before considering the applications of equilibrium constants, let us summarize the important features of equilibrium constants as follows. So first one is what? That the expression for equilibrium constant is applicable only when concentration of the reactants and products have attained constant value at equilibrium states. So for any for expression of equilibrium constant, it is only applicable when the concentrations that are there of the reactants and the products, they have to attain the constant value or at their equilibrium state. Second is that the volume of equilibrium constant, it is independent of the initial concentration of the reactants as well as the products. The equilibrium constant is temperature dependent, having one unique value for a particular reaction represented by a balanced equation at a given temperature. The equilibrium constant for a reverse reaction which is given will be equal to the inverse of the equilibrium constant for the forward reaction. This we have learned that the forward reaction will be the for a backward reaction, the reverse will be the inverse of the forward reaction. So last one is the equilibrium constant K for a reaction is related to the equilibrium constant of the corresponding reaction whose equation is obtained by multiplying or dividing the equation for the original reaction by a smaller integers. Now considering some of the applications of equilibrium constant, we know that it is used firstly to predict the extent of a reaction on the basis of its magnitude. Then we can also predict the direction of the reaction from it, and we can also calculate the equilibrium concentration. Regarding this extent of reaction and direction of reaction is what we are going to discuss in the next video. So that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.